back with structure and interpretation of computer programs. Where is my PDF? Here. Formulating abstractions with high-order procedures. We have seen that procedures are, in effect, abstractions that describe compound operations on numbers independent of the particular numbers. For example, when we define the cube procedure, we are not talking about the cube of a particular number, but rather about a method for obtaining the cube of any number. Of course, we could get along without ever defining this procedure by always writing expressions such as these ones and never mentioning cube explicitly. These would place us at a serious disadvantage, forcing us to work always at the level of the particular operations that happen to be primitives in the language, so multiplication in this case, rather than in terms of higher level operations. Our programs would be able to compute cubes, but our language would lack the ability to express the concept of cubing. And this is connected to what the book was saying in the one of the first paragraphs about that programming languages are also tools to express thinking. This is a very powerful concept, in my opinion. One of the things we should demand from a powerful programming language is the ability to build abstractions by assigning names to common patterns and then to work in terms of the abstractions directly. Procedures provide this ability. This is why all but the most primitive programming languages include mechanisms for defining procedures. Yet, even in numerical processing, we will be severely limited in our ability to create abstractions if we are restricted to procedures whose parameters must be numbers. Often, the same programming pattern will be used with a number of different procedures. To express such patterns as concepts, we will need to construct procedures that can accept procedures as arguments or return procedures as values. Procedures that manipulate procedures are called high-order procedures. This section shows how high-order procedures can serve as powerful abstraction mechanisms, vastly increasing the expressive power of our language. Let's see. Procedures as arguments. Consider the following three procedures. The first computes the sum of the integers from a through b. The second computes the sum of the cubes of the integers in the given range. And the third computes the sum of a sequence of terms in the series, which converges to pi divided by 8, very slowly. These three procedures clearly share a common underlying pattern. They are for the most part identical, differing only in the name of the procedure, and the function of a used to compute the term to be added, and the function that provides the next value of a. These three procedures clearly share a common underlying pattern. They are for the most part identical, differing only in the name of the procedure, the function of a used to compute the term to be added, and the function that provides the next value of a. We could generate each of the procedure by filling in slots in the same template. We could generate each of the procedure by filling in slots in the same template. Okay. The presence of such a common pattern is strong evidence that there is a useful abstraction waiting to be brought to the surface. Indeed, mathematicians long ago identified the abstraction of summation of a series and invented sigma notation. For example, yes, to express this concept. The power of sigma notation is that it allows mathematicians to deal with the concept of summation itself rather than only with particular sums. For example, to formulate general results about sums that are independent of the particular series being summed. Similarly, as program designers, we would like our language to be powerful enough so that we can write a procedure that expresses the concept of summation itself, rather than only procedures that compute particular sums. We can do so readily in our procedural language by taking the common template shown above and transforming the slots into formal parameters. Notice that sum takes as its arguments the lower and upper bounds a and b together with the procedures term and the next. We can use sum just as we would any procedure. For example, we can use it along it with the procedure inc that increments its argument by 1 to define some cubes. Okay. Using this, we can compute the sum of the cubes of the integers from 1 to 10. With the aid of an identity procedure to compute the term, we can define some integers in terms of sum. Then we can add up the integers from 1 to 10. We can also define pi sum in the same way. And using these procedures, we can compute an approximation to pi. Once we have sum, we can use it as a building block in formulating further concepts. For instance, the definite integral of a function f between the limits a and b can be approximated numerically using the formula for small values of the x. And we can express this directly as a procedure. Okay. Okay. Here we see the convergence to 1 divided by 4. Exercise 1.29. Maybe I can do it. The sum exercise 1.30. The sum procedure above generates a linear recursion. The procedure can be rewritten so that the sum is performed iteratively. Show how to do this by filling in the missing expressions in the following definition. Okay. Another exercise. Okay, exercise, 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 exercise. Constructing procedures using lambda. In using sum, as in section 1.3.1, it seems terribly awkward to have to define trivial procedures such as pyterm and pynext just so we can use them as arguments to our higher order procedure. Rather than define pynext and pyterm, it would be more convenient to have a way to directly specify the procedure that returns its input incremented by 4 and the procedure that returns the reciprocal of its input times its input plus 2. We can do this by introducing the special form lambda, which creates procedures. Using lambda, we can describe what we want as okay. Then our PySum procedure can be expressed without defining any auxiliary procedures. So for example, okay, basically we can plug in this lambda special form. Again, using lambda, we can write the integral procedure without having to define the auxiliary procedure at dx. In general, lambda is used to create procedures in the same way as define, except that no name is specified for the procedure. The resulting procedure is just as much a procedure as one that is created using define. The only difference is that it has not been associated with any name in the environment. In fact, define plus 4 is equivalent to define plus 4 blah blah blah. And we can read a lambda expression as follows. The procedure of an argument x that adds x and 4. Like any expression that has a procedure as its value, a lambda expression can be used as the operator in a combination such as this, or more generally in any context where we would normally use a procedure name. Using let to create local variables. Another use of lambda is in creating local variables. We often need local variables in our procedures other than those that have been bound as formal parameters. For example, suppose we wish to compute the function this one, which we could also express as okay, so we have these substitutions. In writing a procedure to compute f, we would like to include as local variables not only x and y, but also the names of intermediate quantities like a and b. One way to accomplish this is to use an auxiliary procedure to bind the local variables. Okay. Of course, we could use a lambda expression to specify an anonymous procedure for binding our local variables. The body of f then becomes a single call to that procedure. This construct is so useful that there is a special form called let to make its use more convenient. Using let, the f procedure could be written as okay, so here basically we are defining the function f that takes two arguments, x and y. We define two local variables using let, and then simply we can plug those local variables inside the procedure described in the definition. Exactly. In the first part of the let expression is a list of name expression pairs. When the let is evaluated, each name is associated with the value of the corresponding expression. The body of the let is evaluated with these names bound as local variables. The way this happens is that the let expression is interpreted as an alternate syntax for lambda, essentially. No new mechanism is required in the interpreter in order to provide local variables. A let expression is simply syntactic sugar for the underlying lambda application. We can see from this equivalence that the scope of a variable specified by a let expression is the body of the let. This implies that let allows one to bind variables as locally as possible to where they are to be used. For example, if the value of x is 5, the value of the expression is 38. Here, the x in the body of the let is 3, so the value of the let expression is 33. On the other hand, the x that is the second argument to the outermost plus is still 5. The variable's values are computed outside the let. This matters when the expressions that provide the values for the local variables depend upon variables having the same names as the local variables themselves. For example, if the value of x is 2, the expression will have the value 12, because inside the body of the let, x will be 3 and y will be 4, which is the outer x plus 2. Sometimes we can use internal definitions to get the same effect as with let. For example, we could have defined the procedure f above as okay. We prefer, however, to use let in situations like this and to use internal define only for internal procedures. Makes sense. Okay, exercise. Procedures as general methods. We introduced compound procedures in the previous section as a mechanism for abstracting patterns of numerical operations so as to make them independent of the particular numbers involved. With high-order procedures, such as the integral procedure, we began to see a more powerful kind of abstraction. Procedures used to express general methods of computation, independent of the particular functions involved. In this section, we discuss two more elaborate examples: general methods for finding zeros and fixed points of functions, and show how these methods can be expressed directly as procedures. Okay, let me see. I don't know if I want to cover this or skip this. Because okay, zero fixed points. I think I will skip this. Exercises. I don't want to do all this math. I don't want to do all this math. Procedures have returned values. The above examples demonstrate how the ability to pass procedures as arguments significantly enhances the expressive power of our programming language. We can achieve even more expressive power by creating procedures whose returned values are themselves procedures. We can illustrate this idea by looking again at the fixed point examples described at the end of section 1.3.3. We formulated a new version of the square root procedure as a fixed point search, starting with the observation that square root is a fixed point of the function, blah blah blah. Newton's method. Newton's abstractions as first-class procedures. We've seen two ways to express the square root computation as an instance of a more general method. Once as a fixed point search and once using Newton's method. Since it was itself expressed, okay. I would prefer to read the general principles of anything instead of having the principles and the important concepts introduced through examples. Especially if those examples are related to mathematics. Because in this way I have to understand the mathematics behind the example, and then I have also to understand the general principle that the book is supposed to illustrate. Instead, I think that it would be better if books could start by describing the general principle, giving the definitions or whatever, and only then providing the examples for these general principles. Because I don't want to read all this math now. As programmers, we should be alert to opportunities to identify the underlying abstractions in our programs and to build upon them and generalize them to create more powerful abstractions. This is not to say that one should always write programs in the most abstract way possible. Expert programmers know how to choose the level of abstraction appropriate to their task. But it is important to be able to think in terms of these abstractions so that we can be ready to apply them in new contexts. The significance of higher order procedures is that they enable us to represent these abstractions explicitly as elements in our programming language, so that they can be handled just like other computational elements. In general, programming languages impose restrictions on the ways in which computational elements can be manipulated. Elements with the fewest restrictions are said to have first-class status. some of the rights and privileges of first-class elements are they may be named by variables, they may be passed as argument to procedures, they may be returned as the results of procedures, and they may be included in data structures. Lisp, unlike other common programming languages, awards procedures full first-class status. This poses challenges for efficient implementation, but the resulting gain in expressive power is enormous. Okay, exercise. A lot of exercises. And we are done. We are done with the first chapter. Okay, so see you in the next video, in which I think I will cover, or either I will cover this second chapter, building abstractions with data, or I will do a video to review the first chapter and to remark important concepts that we have learned. Anyway, see you in the next video. Ciao ciao!